today, and he's going to talk about achieving consensus in static and dynamic regular random graphs. Luca, thank you so much for accepting our invitation, and floor is yours.
Yes, so good afternoon, everyone. Not sure what's the time over there. Great pleasure to be here, honored, and thanks, of course, for the invitation. For me, the Brazilian community, well, I owe a lot, even in my scientific education, to the Brazilian community in many respects. It's always a pleasure to interact with you all. And in fact, for today, I decided, I didn't know the words news of today. Otherwise, I would have preferred perhaps to speak about a different topic. But this is about opinion dynamics. I will not make any comment on real world things and rather focus on the beauty of the maths. So now, what is it about? I selected this topic because there's a lot to do with the Brazilian interactions. Well, in several respects, as I will say. In particular, I will speak about a very classical interacting particle system, the so-called voter model, on certain, well, actually in this talk, apart from the first part in which I will try to give an overview of recent progresses in this area, I will then focus on a specific setting that is quite relatively simple, of regular random graphs, both static and dynamic. So this is based, in fact, with a number of co-authors in these years. I'm looking at this in several questions of interacting particle system on random graph frameworks. In particular, what I will focus especially today is based on two works. One actually that has appeared this year in ALEA, one interaction with the South American and Brazilian community, and another work in progress that is about to appear in a few weeks, I guess. So this is joint work with one Brazilian colleague, Rangel Baldasso, and further colleagues, Rajat Azra, Frank the Hollander, Matteo Quattropani. A few years back, we were in Leiden all together before I moved back to Florence, where I am now. And we started to dig into this business, which, let me make a generic comment, interacting particle system since the 70s of the previous century, there was an explosion of the literature. Still, in these decades, the last 2 decades, I would say there is a beautiful revival of this topic for two main reasons. In one direction, there's a big revival of the theory of a finite state space Markov chain for several reasons. And second, in recent years, we have finally the explosion of the literature, mathematical literature on random graph models, which serve as tools to analyze discrete geometries that are not so symmetric or simple as the complete graph for ZD. So in this respect, we are witnessing in this year big revival of this type of models. So let me get into it. So what is it, the voter model? Well, I will consider the voter model only on finite graphs. So this is a very classical model for simplified model for opinion dynamics in a given population of individuals, wherein each individual essentially can carry one out of two possible opinion, blue or red. So this is a Markov chain based on a graph. You start considering the finite graph. I will only consider finite graph in this talk. Once you have a graph, so the voter model is nothing but a Markov process that I will denote by eta t, that evolves on the state space 0, 1 to the vertex set of the graph. So essentially you start with a graph and an assignment of types. So that's what these are, this eta t, vector of 0 and 1 assigned to each vertex. So vertex here should be thought as an individual. Well, the graph says each individual with whom interacts. And then essentially each individual carries an opinion and may change the opinion according to this Markov dynamics. The Markov dynamics can be described through this sentence. It's rather simple. We can describe it as follows. So each node, each individual has his own exponential clock of rate 1. When this rings, this individual wake up and may want to change his opinion. Will select uniformly at random one of its friends and will adopt the opinion of the friend. So for example, I don't know, this, let's assume that this is the first node that whose clock rings, and then this guy chooses among the 4 neighbors, let's say choose this one with probability 1/4, as only 4 neighbors, and adopt his opinion. So before it was blue, and then it becomes red. So this is a very simple Markovian dynamics on the finite state space at the vertex set of this graph. And we can immediately realize that the structure a bit of this Markov chain, first of all, it has 2 clear absorbing states that are these monochromatic configurations, either all blues or all red. And therefore, it's very natural, and in particular, so this is the finite state space Markov chain that is irreducible outside these 2 states, special states. So it's very simple to realize that in finite time, no matter where the configuration, the system is initialized, in finite time it will converge to what is called consensus. So one of these 2 monochromatic configurations. Now, the interest is in essentially understanding how this Markov chain achieves this one of these 2 absorbing states. Now, in fact, one may look into this time, the first time that eta t is in one of these 2 configurations, so when a consensus is achieved. And of course, the question is not whether it will be achieved or not. For sure, it will happen in finite time. The question is, how does the system reach consensus? And this question can be analyzed in very different refinement and flavor. Let's say first, the first goal would be, first of all, to understand what is the order of this random time as a function of the volume, for example, of the underlying graph. Can we understand more? How about how does this random variable behave as a function of the geometry of the graph? So these are very more refined questions to try to answer, to understand how this system will stabilize in one of these 2 absorbing states. Now, this is the goal, and let me tell you that there's a huge literature about it. And in particular, there are fantastic tools, probabilistic tools to understand this model, and more generally, big class of interacting particle systems. Now, let me in fact recall for the water model a beautiful couple construction of this Markov dynamics, what is called the graphical, very classical construction or representation of this Markovian dynamics. And okay, in this picture, I'm explaining it quite quickly. They should be thought as follows. So on this axis, it's represented the graph. In this case, for the picture, it's just a finite piece of segment, but you can play the very same game on whatever graph. And this is the time evolution, if you like. So this is a space-time picture. So now, how to describe this dynamic? Well, all the randomness you need can be encoded just in a bench, a collection of Poisson processes of rate 1. What does it mean? So assume the graph is, even if the graph can be oriented or non-oriented, doesn't really matter. But let's put it in the unoriented case for simplicity. Still, you assign on each edge 2 independent exponential clock of rate 1, and this in this picture are represented by this oriented arrow. So for each edge, we may have arrival time either in one direction or the other. These are 2 independent Poisson processes, and you do the very same for each edge in this graph. So you have this field of random errors, independent collection of Poisson errors, and this is truly sufficient to describe the entire dynamics of the voter model, if plus you specify what's the original state of the configuration at time 0. In fact, the interpretation would be simply that whenever a clock, an oriented edge rings, so for instance this arrival, this guy here at this time will adopt the opinion of this guy that is here and will change. In particular, this is nice because we can follow backward. So at a given time t, if we want to understand what's the state of the system at time t, we simply have to look backward into this Poisson errors representation, and we can reconstruct what is the opinion of any guy, for example, this eta t1, so at time t, the individual one, will have the opinion that was carried at time 0 backward in time from this original guy 2. So this graphical representation allows, therefore, to trace back the origin of each opinion. And in particular, we notice that even backward in time, this is nothing but a path of a random walk. In fact, this graphical construction is open up a number of tools to analyze in detail this system. And in fact, let me tell you that, well, you can make this precise algebraically. Chiara knows a lot about it. But for example, so this voter model, it's in a precise sense dual to a system of coalescing random walker. To make it short now, let me just tell you that when we look backward this space-time evolution of these arrows, we can use the very same randomness to sample a system of what are called coalescing random walks on the given geometry. So in fact, you see here I simply left the realization of the Poisson arrows, and now if you assume that you start at time t putting a random walk on each side, then you simply follow, so this is the system of coalescing random walk, the arrows backward in time, and the system of coalescing random walk is simply that when two such lineages merges, they keep on traveling together, and this is this red trees that you see appearing and coalescing eventually. So this is beautiful because system of coalescing random walk in itself is a mark of a dynamic that it's of interest to be studied, but essentially gives a way to control right away the consensus time, at least bound for the voter model, using this dual process of the system of n coalescing random walkers. In fact, if we define for the dual backward system of the coalescing random walkers the coalescence time to be the first random time that all these n particles are merged, then we can realize immediately by construction that this gives an upper bound on the consensus time of the voter model itself. In fact, if you like, if we look forward in time, this red picture, this means that this guy, his opinion that was, I don't know what it was, either blue or red at time 0, let's say red, has managed by this time to invade the entire graph. Okay, so the smaller or equal is, it could be that, for instance, the system, it's initialized in a way that it's already at consensus, so we don't have to wait the full coalescence to happen. So it's just a bound, but it's a bound that tells a lot on how to put the finger on this consensus time. In fact, well, let me tell you one more thing. So if we are willing to study consensus time dynamics, then there's another very important observable related to the voter model, and it's what I will call the set of discordant edges. So what are those? This is a set evolving over time, dt, and it's simply the set of edges that at time t carries, the voter model carries a different opinion at the extreme of these edges. Now, if you think this is nothing but the set describing, if you like, the perimeter of the discordances between the blue and the red region of the graph. And in particular, of course, when this set becomes empty, that means consensus, right? And in fact, when we study, for example, a single edge at time t, we ask ourselves, what's the probability that the single edge is discordant? Well, let's assume that we initialize the system with the Bernoulli product measure at time 0 with the parameter u. Well, it's very simple to understand that in order for an edge at time t, so this one I'm picturing here, this edge with the extreme xy, how can it be that this edge is discordant, so that there is an opinion blue on one head and red on the other extreme of the edge? Well, it must be the case, first of all, that in the backward construction, until time 0, the two lineages of these two random walk, they never met. Otherwise, they would have the same opinion at this time. And second, it must be the case that at time 0, the guy that carried the opinion at this time t here to both of these extremal edges were having a different opinion. So this is captured in this very simple computation here. And in particular, we realized that for an edge to be discordant at time t, if we started from Bernoulli, is nothing but, okay, this factor of two quantities. There's one quantity that is simply the initialization that we are asking that these two Bernoulli random variables are different with parameter u, and that's what this quantity is capturing. And on the other hand, we realize that an important quantity is the tail of the meeting time of two random walks. That's what this is. This tau meet xy is the time, the first time that two random walkers start from x and y will meet. And in order to be discordant from this construction, we see immediately that it must be the case that they have not met yet. Okay, so having explained that, I may now want to refresh you a bit of a beautiful part of this theory that has emerged in these last years. I'm happy, actually, one of the main contributors is present here, Roberto in Buzeiro. Anyhow, let me try to sketch you, to briefly recall you part of this beautiful part of the literature. So, well, let me mention one other thing. This model, of course, initially has been studied a lot on the complete graph and on finite graphs that are growing on finite boxes of the ZD. In particular, on the complete graph, analyzing the system is particularly simple. This is a model actually used a lot also in genetic population. It's called the Moran model. And on the complete graph, this system is rather simple. We are on a mean field the finite geometry. And if you analyze the density of blue opinion in this graph, you will realize that this is a very easy martingale that can be reduced to a birth and death process. And you can study essentially everything and understand very well how consensus is reached and so on. So in recent years, people started to, well, actually also in the original, around the 80s and 90s, many people started to understand Aldous field, Durret, many others, that essentially the analysis on the complete graph could have been lifted to other geometries. And now in these years, this has been made more precise, in a sense, I would say. And we can speak, I don't know, about sort of mean field theory for growing sequence of graphs. So let me try to describe you this, what I mean by that. So a key quantity to understand these models in general is, it turns out to be the first meeting time of two independent random walkers, as I just described you, that is related in a sense with discordances. But in particular, when these two random walks start from the invariant measure pi associated to the given graph. So let's assume that we are on a graph that is finite, strongly connected. So the random walk on it is irreducible, aperiodic, and there's a unique invariant measure pi. So that this quantity is well defined. Now, why this is a key quantity to understand this system? Well, at least is a key quantity to understand it deeply on certain classes of geometry that include the complete graph, but goes much beyond that. So let me try to sketch you here what I mean by mean field assumption. So let's assume that we have a sequence of graphs. In particular, this is true for the complete graph, but for many other graphs, provided that the single random walk associated to the graph satisfy two properties. First, its invariant measure is not too concentrated. I'm a bit not precise here because I want to recap the main results. But you should think here, for example, that pi is close to the uniform measure, or that at least there are no sites with really a macroscopic mass on it. It's a mild condition, if you like. And the key second condition to say that the behavior that we understand on the complete graph can be lifted to the other geometry is the following. Assuming that the mixing time of the walk, that is nothing but the worst case in total variation distance of the first time for which the distribution of the walker will be epsilon close to the invariant measure, so the very classical mixing time. Of course, the scales with n, with the size of the system. If we are on a sequence of graph for which the mixing time divided by the expectation of this quantity, the meeting time of two random walk, where two independent random walks starting from stationarity, if this ratio goes to 0, then that's what we would call mean field geometries. Of course, this is very simple to check that this is the case on the complete graph. Complete graph random walk mix in two steps, well, depends how you define the random walk, but let's say infinite number of steps. While the meeting, you can show that is of order n. So this quantity decay goes to 0 like 1 over n. But for any other geometry for which you can check these two assumptions, then let me briefly recall you two theorems that have appeared recently. One, as I mentioned, is, beautiful work of Roberto Ibuzair Oliveira, 2013. Actually, he had a couple of works. And here I'm stating a simplified version of his theorem that is more general. Anyhow, under these two assumptions, Roberto showed that the coalescent, so I would say the work of Roberto is mainly a work about the coalescing system of random walkers, very detailed analysis of it in relation to generalization of the finite Kingman coalescence, this type of things that were a bit classical on the complete graph. And it says that essentially the coalescing time, the time it takes a system of n coalescing random walkers in this sort of geometries, if the right scaling is truly the mean of this expected meeting time from stationarity of two random walks, and in particular, if we scale it according to this sequence, then we would converge to an explicit random variable that, okay, it comes from, it can be interpreted as, so is a sum of independent exponentials, is a series actually for k going from 2 to infinity, which would correspond essentially to the merging of two lineages in the k in this infinite say coalescent system. And in particular, out of this result, we see that the mean coalescing time of two random walker is nothing but asymptotically twice the time it takes for two random walk from stationarity to meet. So this is somewhat special of this sort of geometries that have good expansion properties, if you like. And this theorem answered the question of the scaling limit of the coalescence time of the Volter model on these geometries. And second theorem, more into the direction of the consensus time, I lifted here from two papers. One is the work again of Roberto, who proved that even for the consensus time for the Volter model when starting from Bernoulli, there is a very similar thing. The right scaling is given by the mean of this meeting time from stationarity. That's why this is truly a key quantity to be understood. And again, if you scale it like that, you will converge to an explicit random variable which in this case is morally similar to the previous random variable, except that is a truncation of the previous sum, which takes into account the random initialization of the Bernoulli in the system of in the voter model. So if you, as I said before, depends. You may be already at consensus at time zero if you sample a weird configuration of Bernoulli, and that's in fact this different constant here, which essentially is the entropy of a Bernoulli. Anyhow, Roberto results answer therefore the question of the scaling limit of the coalescence time and the consensus time in the voter model for this sort of geometries. And then there's another very nice work that I would say is truly for the voter model, and it's a martingale sort of analysis of this system. Chen, Choi, and Cox in 2016, they wrote a very nice work paper in showing what was known already for the complete graph and for a number of things of other systems, namely that when we look at the opinion, the density of opinion of blue opinion, let's say in the voter model at any time t, well, it's not difficult to see that this is a martingale. The interesting thing, and actually the predictable quadratic variation of this martingale, for those that are familiar with this object, can be expressed in terms of discordant edges. And now what Chen, Choi, and Cox did, they proved that under the previous mean field condition, so pi not too concentrated and mixing path with respect to this meeting time from stationarity, well, this martingale stabilizes and converges to a limiting classical martingale that is the so-called Wright-Fisher diffusion. So this is nothing but the Wright-Fisher diffusion is this diffusion process here, if you like, this martingale-Ito diffusion process, which is nothing but a Brownian motion with the variance on 0, 1 on the interval. So this is density, or is controlling the density of opinion. With this, say, volatility or variance that is, of this form, yt, 1 minus yt. This is also called sometimes genetic variability. If you think that yt is a sample of an individual, what's the probability that from an infinite population that carries a given type? And yes, so this means that this system of opinion, the thing is only at the scale of this mean meeting time, stabilize this martingale, and it becomes approximable, so can be approximated by this Wright-Fisher diffusion. So this clarifies also at this time scale how this system in a large scale behaves as a process. Now, I'm not specifying here this convergence is truly the convergence of the entire process for any t from 0 to infinity. So it's in a Skorohod topology, the very classical type of in Kadlak space convergence of these processes. Good, so that's what I briefly wanted to discuss of this general theory. Well, now, I hope I convinced you that, therefore, in view of these very nice results, it's very crucial to put the finger on this tau meet from station, so the first time, this quantity. The first time that two random walks starting from stationarity that are independent, they will meet in the given geometry. And in particular, the mean of this quantity is really the sequence that allow you to derive all this sort of result. Now, these are very general results. Problem is on which explicit model, graph model, we can put the finger on this sequence. So this is a different question that is much more model dependent. And in fact, so let me now discuss this. Meeting of two random walk from stationarity, this quantity. Well, this has been studied in the literature, first of all, as usual, on the complete graph and on the finite boxes of ZD. This was proven quite some time ago, how this expected meeting time from stationarity of two random walks really asymptotically is in first order with explicit pre-constant. And for a while then, the literature, okay, there were very many other works in estimating at least the order of this quantity, and even in these days, there are very different work trying to capture at least the order of this quantity in view of the theorem I told you before. But as I said before, at the very beginning, now that we have lots of frameworks of random graphs, we can hope perhaps to prove in this sort of geometries very precise results on how this important sequence behave. And this is in fact what has been done actually originally in 2005 by Cooper and Fritz, that they were analyzing very different questions of cover time and so on. So they proved in now a random geometrical setting, in the setting of the regular random graph. So this is simply the random graph on n nodes that is sampled uniformly among all the possible graphs on n nodes that are deregular. And for this type of random graph ensemble, Cooper and Fritz could prove that this expected meeting time from stationarity, it's linear in the size of the system, and they could actually pull out the explicit constant depending on D. This was it for a while, and now, as I said, lots of people have been proving a similar statement, but not as precise. And as far as I know, these were the only cases in which this pre-constant was explicit. And let me advertise a very different work that has appeared this year, actually a few weeks ago in Annals of Applied Probability, that with Rajat, Matteo, and PhD student that we are co-supervising with Rajat, Federico Capannoli, we recently made clear also how this meeting time we could pull out this constant, well, again, in the context of directed random graph that can be sampled out of the model, the directed configuration model, for those that are familiar with. Now, in particular, now I don't have time, this is a very different work, but let me encourage you to have a look at it. I think this is a very cute work, even for very practical purposes for applied people, because it's the first example in which we have a very explicit functional of this constant in terms of the degree sequence of the graph. And therefore, we can understand that, for example, in this geometry for which you know what is the degree distribution, and it's the only example where it's not regular, we can really understand how much the meeting is fast, is slowed down or sped up as a function of the degree structure. And in particular, we could make more precise even some prediction by physicists about this non-regular finite random graphs. Now, that's not what I want to talk about today. Today, I want to focus on this finite random graph models of deregular random graphs. As I said, there was known already the explicit meeting time, how it behaves, the explicit constant in this case. And in particular, this is a geometry that fulfills the mean field assumption of Roberto and Chen, Choi, and Cox. And therefore, essentially, it's also known that if you speed up by this constant, you converge to the Wright-Fisher diffusion at time scale n. Now, what have we done and what I want to discuss in the second part, in the remaining, I don't know, 20 minutes or so. What are we doing? What we have already done in one first paper, and what we are about to finish now for deregular random graph. So, deregular random graph here, there's an example because it's a delicate ensemble. If you fix n, you realize, for instance, that in order to have a non-empty set of deregular random graphs, you need to have some constraints, like, for example, that n, the number of edges, and d divided by 2. So n times d must be even. Otherwise, you simply cannot build this sort of graphs. And okay, there's an interesting literature even in accounting. There's no explicit formula to count for a given n how many such irregular graphs exist. Anyhow, it exists. This is a non-empty set and can be studied very much in detail, in some details. And when I speak about a random irregular graph, it's simply the uniform measure over the set of the regular graph of with n nodes. An example is pictured in this picture. And so what have we done on this random geometry? We have studied a bit more in details. Actually, we reproved this result of Huber and Fritz in a different way, but we studied even more in detail, and in particular, we understood also better what happens before the consensus time scale, as I will try to tell you. And the second main thing is we started to add to this list another example where we can pull out the explicit constant. That is the case when these graphs are not just random, but they even evolve over time. This is a very different sort of challenge because the theory I discussed before is for static graphs. So it was not even clear a priori whether this could be lifted to dynamic graph. And the answer is yes, provided the right graph structure. So let me try now to discuss that. And okay, and in particular for the static, the regular random graph, as I said, this was known explicitly, and this constant theta of d depends on what is your constant d. That is, every node has degree d. And it's this explicit constant, d minus 2 divided d minus 1. And in particular, we can rewrite the Wright-Fisher approximation in this form. So before I said that when you speed up by the meeting time, now I simply pull out the number n, so on linear time scale, and this constant appears in the diffusivity constant of this Wright-Fisher diffusion there. So in this case, it's explicitly known also the diffusivity constant of the Wright-Fisher diffusion. All right, now I can dig a bit more into these two results that we're studying with Rangel, Rajat, Frank, and Matteo. So, voted on static and dynamic irregular random graph. So, what can we say? So, as I said already, so the static ensemble of the irregular random graph is nothing but a random graph sampled on n nodes. For every n you can define it, is a random graph sampled from the uniform measure that I will denote mu d over the space of all d regular graph on n vertices. Instead, I will also talk about dynamic irregular random graph ensemble. What is it? Well, we can study this under proper assumption on the dynamics. In particular, here in the work that we are about to put public, we studied a dynamics that is somehow a bit special in the sense that, first of all, is a Markovian dynamics in which the graph you sample at time 0, well, it's a rewiring edge dynamics with an explicit parameter nu that tells you the speed of the dynamic. And in particular, this dynamic, first of all, so you sampled at time 0 a given graph from the uniform measure of a d-regular random graph. So you sample one such random graph. And this dynamic is a dynamic that will be invariant under this law. So will preserve the number of edges. And in particular, will also be reversible. And how is this dynamic defined? Well, let me give you a simplified version of this dynamic. Actually, this dynamic was already studied a few years back by Huber, Greenhill, and some other, and more recently, even Roberto, Daniel Valesin, and Shapira studied the contact process on this dynamic ensemble. So this, in a sense, is the first work in which the voter model is considered on this type of dynamics. And the dynamic is as follows. So there's this parameter nu. We have sampled a given graph, the regular graph, on n nodes, and each edge has a rate nu and when its clock rings, this edge selects uniformly at random from the universe of all the other edges, one of them, and rewires, and it makes, so when this clock selects another yellow one, simply these two edges are rewired. In reality, we describe this dynamic over half edges with rate nu over 4. Doesn't matter, it's just more technically involved, the precise description. What I just wrote on this slide, I think for all of you should be clear, and that's asymptotically equivalent to what we are truly doing. So, okay, so what did we study about the voter model on this static and dynamic regular ensemble? First of all, let me briefly tell you what we did for the static, and then I will tell you what we did for the dynamic. That is way much harder for several reasons, and innovative, I would say. Okay, so static, the regular ensemble, I already told you, was known for a while, the explicit first order asymptotics with explicit pre-constant of the expected meeting time. And what we studied better this set of discordant edges. And in particular, we studied this quantity, the expectation of the density of discordant edges. So this is the set of discordant edges. This ratio here that I'm pointing here is nothing but the cardinality of this set divided by the total number of edges. M is the total number of edges. Therefore, this is the density of discordant edges. And we studied the mean with respect to the voter when initialized from Bernoulli of parameter U. So this quantity, of course, is a random quantity itself, this mean, because it depends on the underlying geometry that is random, that is sampled from mu of D, from the uniform measure of the regular graph. So what we proved, we proved a general formula that it's valid at all time scale for this mean number of density of discordant edges. And it turns out that this random variable for any time scale Tn converges to this sequence. Now this sequence, let's look a moment at it. It's composed by 3 factors. The first factor is just what I showed you before, is the paying of the Bernoulli initialization of the Bernoullis. The last exponential factor is something where it appears this constant theta of D. And notice that this depends on the time scale. It's times Tn divided by n. So this exponential factor is different from 1 essentially only from linear time scale n. So if Tn is sublinear, this is essentially 1, this number. And the other important factor is this Fd of Tn. What is it? This is nothing but the meeting time of 2 random walks starting from a given edge on an infinitely regular tree. So this quantity is the tail of this meeting time. Now, in fact, this sort of random graph ensemble, they are sparse and they are locally tree-like in the sense that in the Benjamin-Schramm topology, for those that are familiar, if you start exploring any given nodes until a depth, say, its neighborhood until a depth, say, log n, you will realize that can be perfectly coupled with a tree. You will not see loops. And in particular, for this deregular random graph, it's particularly simple because this local width limit of this geometry is nothing but a deterministic geometry. It's just nothing but an infinite deregular tree. And on an infinite deregular tree, you can compute explicitly this quantity, that 2 random walks starting from an edge will meet after time t. It's just, you see, if you think for a moment, you can just study the difference of 2 random walks on this infinite deregular tree, and this becomes essentially a birth and death chain that you can explicitly study. And so consequence of this theorem is that we made clear the discordant edge is this average, that it behaves differently in the different time scale. In particular, we have, if you like, 3 different regimes. So the time scale n is the time scale at which was already known that the Wright-Fisher diffusion approximation kicks in. And in fact, what you see here is nothing but the mean of the Wright-Fisher approximation, of the Wright-Fisher diffusion. While on, there's an interesting fact about the discordant density of discordant edges, so this perimeter of the discordances, that on order 1 time scale, they are simply driven by this tail of the first meeting time on this infinite tree. But then, as soon as the time scale Tn in which we are observing is divergent, but is sublinear, then it's stabilized to a plateau. And only at time scale n, in a sense, the system, the interacting system of opinion realized that it's no longer on the local geometry. There are cycles, and the martingale, underlying martingale stabilized, and the Wright-Fisher diffusion kicks in. So this is a bit of what we did. So in particular, we made clear out of this what happens before the time scale n, that is the Wright-Fisher time scale, for this system. And in particular, we even show that before the time scale n, that is when the Wright-Fisher diffusion kicks in, the density of discordant edges is really concentrates very well. So it's essentially epsilon close to this mean, which and it's a uniform concentration. Okay, so in a picture, what we just did, what I just explained, is this picture here. This is a real world, is a simulation, is a numerical experiment. What do you see on this picture? So, first of all, this picture, the blue part is the evolution of the density of opinion of the voter model on this irregular random graph. And okay, here it's the time step of this evolution of this density is such that you can really see the different behavior. So in fact, I mean, in this picture, this simulation has, I don't know, 10 to the 6 time steps. And essentially what it turns out that the time scale of the Wright-Fisher diffusion is about this point I'm pointing here. And in fact, here you really see the diffusion. This is the Wright-Fisher standard diffusion here, this blue part here. While before that, this is truly the, if you like, the sublinear time scale. So times of order, little order n, in which the opinion dynamic is still a martingale, but it's not the right martingale that has the, can be approximated by the Wright-Fisher diffusion. That's why we see at this initial part that is behaving a bit differently than from the Wright-Fisher diffusion here. So the theorem I just showed you that we proved for this regular static ensemble essentially made clear the picture of this orange curve, which is the simulation of the density of discordant edges. And in particular, what you can see here is that, well, now I will zoom you here. This perhaps is one of the main novelty that we really show that this density of discordant edges, this random variable, is very well concentrated to this mean, and this mean here for order of time 1 has its own behavior, and then it's stabilized to a constant plateau here. So you see here, this is essentially constant. And only around this time, the system realized that there are cycles, is not on an infinite tree, and therefore even the discordant density starts to behave as a function of the Wright-Fisher diffusion and starts to get out of this constant plateau. This we can see it even in more detail. I mean, this is a zoom in of this simulation on the orange curve. The initial time scale that are the sublinear, actually these are order 1 time scale. The red line here is the theoretical curve that we computed, the asymptotic mean of this density of discordances. And here you see really the simulation of the density of discordance that actually concentrates very well. So it's really stick to this theoretical curve and reach the plateau here that would correspond to this line here. And then we'll stay there until order n, and then we'll get out of this plateau. So this is the sort of quasi-stationary behavior we made precise in this deregular static ensemble. Now I see that I have very limited time yet, but let me tell you just 5 minutes more on the dynamic, what happened on water on the dynamic deregular ensemble. As I told you before, the dynamic is simply the same, very deregular. Now every edge has its own rate nu, and this edge, when it wakes up, choose at random another edge from the graph and rewires with it. So this is the dynamic. We are studying the water model on this dynamic. Now, it's very unclear whether this entire theory that I described you can be lifted for this dynamic setting. And the answer is yes, provided that the dynamics is amenable to do computation, and in particular is stationary with respect to the invariant measure of the static ensemble. So what we have done here, we did essentially two main things in for the water on the dynamic deregular ensemble. First of all, we put the finger explicitly on this dynamic ensemble on the meeting time of two random walks from stationarity. So this is this theorem is in itself, I think, of interest regardless of the water model. What's the distribution of the meeting time of two random walks from stationarity in this dynamic random graph? Well, we proved what was analogous result of what is usually done for static graphs. So namely that this meeting time at scale n behaves exponentially, can be approximated by a truly an exponential distribution. Here you really see, again, a simulation on this dynamic of the distribution of this meeting time when speed up at time scale n, that is the size of the system. And we could put the finger explicitly on the constant, on this diffusivity constant, analogously as it was done for the static case. Now here it's much more, it's much harder to prove this result. In fact, this I think is the major technical contribution we're doing in this work, and innovative, because it's done through, okay, and in particular we get a formula for this diffusivity speed, which is expressed, okay, you don't have to understand here, is expressed in terms of a weird continuous fraction, but that we have it explicit, we can analyze it, and in particular, for example, we see that as a function of the parameter, this is the number of degree of each node. Nu is the speed of the dynamic, is the rate at which edges in the graph updates and rewire. And we proved that this constant is strictly increasing. And well, we have more, but let me just mention you that. And in particular, we really see that this model interpolates between the behavior on the complete graph and on the static random geometry, the regular graph. Because when we take the limit of one of these two parameters, nu to infinity, or the dimension of the degree to infinity, we recover really exactly the constant known for the complete graph. On the opposite, when we send the speed of the dynamic to 0, we recover the constant of the static random graph. Okay, so in this work on the dynamic, I have to wrap up, so let me mention you. This is perhaps the most innovative first result. The second one is that we looked, let me just mention it very briefly. The second theorem is we looked more at the evolution of the water model on this dynamic random graph. And in particular, we proved that the entire program that I discussed before of Roberto and Chen and Choi and Cox, for example, holds also in this that is valid only for a static random graph sequence or sequence of graphs under that mean field assumption. This is still valid for this dynamic random graph. And in fact, we proved that if we study the discordances of the water on this dynamic deregular random graph, then we can prove a very analogous result of what I showed you before, that on a short time scale, this stabilized to a plateau, which is driven by the constant I just showed you, that can be made explicit. And second, that only on linear time scale, the discordant edges, the integral, converge to the right integral, that is the predictable quadratic variation of this right-Fisher diffusion. So even for the dynamic, the regular graph under this rewiring reversible dynamic, all this program is valid, can be made explicit, and we have this constant that can be studied in details. Now, in light of time, I would perhaps stop here and just mention that where does this constant come from? This is actually very involved, but in a sense, it's reduced to studying, well, you can couple the system on the dynamic random graph on a much simpler system, provided you can do the coupling, and it's very technical, very quite a lot of work. But essentially, you have that locally two random walks, either if they are near in the graph at a given time, either they feel like if they are on an infinite tree, like for the static case, except that the dynamics then can affect the arm of the tree in which they are walking to meet. And therefore, we can couple essentially the true system with a system of coalescing and merging trees, in which on these two trees there are two random walks that tries to meet or not. And in few words, that's precisely how we managed to get that continuous fraction explicit expression for this diffusivity constant, and to clarify this picture on this ensemble of the regular graph that are also dynamic. That's all I wanted to say. Thank you all for the attention, if you're still with me.
Many thanks. Let's see if there are questions or comments from the audience.
Luca, do you think the dynamic random change, dynamic change can be carried out to something like the torus and dynamic percolation or some other context, or it breaks completely if it's not tree-like?
So, very good question. What I think is, of course, you can study the very same dynamic on other geometries and the water model on this dynamic random graph, but the picture will be completely different in terms of the behavior that will emerge. I mean, for example, already now you mentioned I don't know what exactly you mentioned, perhaps you mentioned the D-dimensional torus, right? Okay, if you rewire the D-dimensional torus according to these dynamics, you will in very short time destroy completely the initial rigid geometry. And so depends on the dynamics where it will converge to the underlying geometry, and then you can try to study that. So the detailed analysis that we did is really tailored to this deregular graph, because we can check all the statistics and make it so explicit. More generally, I think for sure you can study other geometries, but you will not get the very same structure. For example, if you are on the torus, notice that the torus already in dimension 2 does not satisfy the mean field assumption I was saying before. But still, you can play a very similar game, but it's rather clear that depending on the geometry, you may adapt part of what we did or not. I'm not sure if I have answered exhaustively your question.
Yeah, thanks.
Let's see.
Well, more generally, I think whatever dynamics that is reversible and invariant that might be slightly different from what we did, for sure it goes through.
Luca, I have a question. Pablo. I didn't understand what is the distance that you are using between the two random walks, because you are in the tree, but you transformed that in one dimensional. How do you do that?
That's a very good question. So studying this, if you like, a short answer to that is this goes back to Aldous, how was it called? Clamping heuristic. So when you want to study the meeting time of two random walks from stationarity, essentially studying the meeting time of two random walks, you can look at the product graph, and it's a question of the hitting time of the Markov chain on the product graph on the subset, diagonal subset of points XX, right? That's what it means. That okay, now this is a matter of hitting time distribution from stationarity of a random walk on a graph that needs to have the right structure. And there are a number of tools to do that due to Aldous, and I mean, there are different heuristics. Now, in the static, the regular graph, we did that through what is called the first visit time lemma, that essentially tell you that what you have to capture to study the parameter of the exponential random variable that approximate your distribution of the heating time, you have to study the local time of this random walk on the product graph up to the mixing time, and if you can put the finger on it, that this is sufficient to characterize this this exponential law of this meeting time. This is rather standard, and we used this sort of tool in the static case. In the dynamic, we had to reprove by hands via a very complicated two-step coupling procedure that you can mimic a similar story. So we cooked it up ad hoc for this dynamic ensemble. And we crucially use the fact that is also true in the static, that these geometry are locally tree-like. So two random walks, if they are close, you know how to compute the distribution of their meeting time or the statistics. The problem is when they go far apart, that even the local tree structure can no longer be used. The fact is that you are on a geometry in which this walker mix fast. So therefore, they are mixed if they are far apart, and you may restart the game. So that's morally.
Okay.
I'm not sure.
Okay, so did I understand correctly that you are using the expected hitting time of the boundary as the distance?
Yes, in a sense, it's what is, yes, I would say so. Yes.
Okay, and then you have to bound because it's something that is not constant because the graph is not one dimensional, so you have different hitting times. Okay, how to study better. Thanks, Luca.
Let's see if there are more questions. Comment, I think that's not the case. So let's thank Luca again. Thank you, Luca, and we update next Wednesday.
Thank you all,
everyone.
Ciao, Luca.
Thanks, Luca. Bye, guys.
Bye bye.
We will see soon each other. Bye. Muite saudade. Ciao.
Ciao, ciao.